Hello children, today we are solving the numericals on the second topic of chapter 1 of class 11, units and dimensions. Before we get to solving the numericals, let's see why learning about this topic is important for us. Dimensions have a lot of applications in physics, and some of those are it is used in deriving formulas. It is also used in finding the units of many physical quantities. It is also used in checking dimensional consistency of many expressions. And these are also the types of questions that we come across in this topic. So now let's get to solving the numericals. The first one here is time period t of a simple pendulum depends on its length L and gravitational acceleration g. The dimension of time period t is four options are given. Before we find the dimensions, we need to know the expression for time period of a simple pendulum, and the expression is t is equals to 2 pi under root L by g. This is the expression. We can ignore 2 pi as these two do not have any units, so we will only use under root L by g for finding the dimensional expression for the time period. So RHS is under root L by g. It can be simplified as L to the power half and g to the power minus half. Then when we convert them into their dimensional expressions, we can write L to the power half and g is gravitational acceleration, and the dimensions of acceleration are Lt to the power minus 2. These are the dimensions of acceleration. So we will be using this in the expression Lt to the power minus 2 to the power minus half. On further simplifying it, we will get L to the power half, L to the power minus half, and T to the power minus 2 and minus half will give us 1. And here we have half and minus half. These two will cancel out and these two will give us 0, and anything L to the power 0 is equal to 1. So this will be 1 into t to the power 1. So the final answer is t. So our answer is B option. For the next question, we have the dimensional formula of velocity is, we have four options. Now velocity is B is equals to displacement upon time. For finding the dimensional formula, we can just write the dimensional expression for displacement, which is L, and for time it is t, and this gives us L t minus 1. This is the answer, and C option is the correct answer, L t minus 1. Now for the next question, we have which of the following equations is dimensionally correct. We need to check the consistency of these equations. As I told you that it has many applications, and one of those is this. Now the first one, A. Let's solve it. The expression is S is equals to ut plus half at square. So we will tackle the LHS and RHS separately for these questions. Also, we must know one rule of homogeneity, which says that whenever addition or subtraction is used in any expression like it is used in A, then all of the separate terms will have same dimensions. These separate terms will have same units, same dimensions. Okay. Now, getting back to this, first one is S is equals to ut plus half at square. This is the expression. LHS is very simple. LHS is S and the dimensions for S is L. Now we need to find the dimensions for ut and dimensions for half at square. We will only find the dimensions for at square. half is a number, it doesn't have any unit. So for RHS of A, we have UT, and dimension for U is L T minus 1, and dimension for T is obviously T, and when we further simplify it, we will get L. This and this cancel out. Now for AT square, dimensions for acceleration, we just discussed it in the previous question, L T minus 2, and it's better if we learn the basic dimensions of displacement, um, velocity, acceleration. It comes in handy in solving the numericals. Getting back to the question, dimensions for T square. Okay, now these two cancel out and we get L as the dimensions for AT square. This and this are similar, so the first expression is dimensionally correct. Now B. For B, on LHS we have F and dimensions of F. Before dimensions, let's see the formula. F is mass into acceleration, and we can find the dimension as m, and for acceleration we have L T minus 2. So it becomes m L T minus 2. Now for RHS, the dimensions for mv square, we have m for mass, and for v square we have L T minus 1, minus 1, T minus 1 square. So this becomes m L square T minus 2. Now let's check the consistency, and mlt minus 2 doesn't match with ml square T minus 2. So these two are not similar. This is not correct dimensionally. Now for the third one, C question. We have E is equals to half mv square. We will ignore half because half doesn't have any units. So we will just check E and mv square for the dimensional expression. The dimensional expression for energy comes out to be m L square T minus 2. This is the dimensional expression for energy. We have to match it with mv square. If it matches, then the answer is correct. For RHS, we have mv square, and this is equal to m L T minus 1 square. So this comes out as m L square T minus 2. We can see that these two expressions are exactly the same. So the third one is correct. Now let's solve the next question, question number 4. Question number 4 says a quantity x is equals to L square by T3, where L is the length and T is time. If the SI unit of L is meter and T is second, the SI unit of x is, we have to find the SI unit of x here. It is very simple. X is equal to L square by T cube, right? And SI unit of L is meter, so meter square upon T is, the SI unit of T is second, so second cube, and this becomes m square s minus 3, and the answer is C. Now next question, fourth one was very easy to solve. Fifth one is the frequency f of small oscillations of liquid in a U tube depends on 3 things: gravitational acceleration g, density of liquid rho, cross-sectional area of the tube A. The frequency f is proportional to g to the power a, p rho to the power b, and a to the power c. We have to find the values of a, b, and c. It's very simple to solve. We do not even need to know how the oscillations of a liquid in a U-tube work. We just need to know the basics of dimensional analysis. And the question is already helping us in finding the answer. It has told us that the frequency is proportional to g to the power a, rho to the power b, and a to the power c. We will use this information to find the answer. So frequency is f, and it is proportional to g to the power a, rho to the power b, and a to the power c. We are going to use this expression to find the values of a, b, and c. We can equate this by including a constant. So we are assuming that our constant is 1, and now this expression becomes g to the power a, rho to the power b, and a to the power c. You can assume the constant to be k, but it becomes simpler if we just assume it to be 1. Now let's solve the LHS and RHS separately. For LHS we have f, and frequency is equal to 1 upon time period. So the dimensional expression for this becomes t to the power -1. Let me write it again. It becomes t to the power -1. Now RHS is also going to be simplified here. For RHS we have g to the power a, rho to the power b, and a to the power c. G is gravitational acceleration. So if we simplify it further, we can write L t to the power -2 as the dimensional expression for gravitational acceleration. It's just same as acceleration. Then rho is density. We know that density is mass upon volume. So for density, mass upon volume expression helps us in finding the dimensional formula. M volume क्या हो जाएगा? Volume हो जाएगा L into L into L. So this gives us L -3, right? So M L -3 for density, and then in the end we have A, area. So L square to the power C. This is the expression we are getting. Now we will simplify it further, and after simplifying it we will get, let's simplify it over here only. After simplifying it we will get L to the power A, T to the power -2A, M to the power B, L to the power -3B, and L to the power C. If we simplify it further, we will get L to the power A plus 2C minus 3B, M to the power B, and T to the power, here we have T to the power -2A, and when we further simplify it, we get M to the power B and L to the power A plus 2C minus 3B and T to the power -2A. This is the final expression. Now when we compare this, because there's an equality sign between these two, so when we compare this with the dimensional expression for frequency, we will be able to find the values of A, B, and C. For the dimensional expression of frequency, we can also write m to the power 0, L to the power 0 and t to the power minus 1. Why are we doing this? We are doing this so that we can find the values of A, B and C. Since this expression, the expression for frequency doesn't have terms for m and L, so we can assume that they have the powers of 0, right? So now let's compare these powers with the ones we have got in RHS. So first one is m and the power of m is b, right? And when we compare the power of m on RHS and LHS, we will find out that b is equal to 0. इसमें solve ही नहीं करना है, we are getting the answer directly. Now for the second one, t, the power of t is minus 2a, and when we compare this with the power of frequency, we are getting minus 1. So minus 2a is equals to minus 1 and a is equals to 1 by 2. Now the third one is power of L, a plus 2c minus 3b is equal to, the power of L in the expression for frequency is 0. Here we have seen 0. So we will compare it with 0. This is equal to 0. And hence we will solve it further. A plus 2c minus 3b. We will put the values of a and b in the third equation and we will get half plus 2c minus 0 is equal to 0. When we will solve it further, we will get c is equal to minus 1 by 4. These are all the questions for the day. Thank you.